viewers at home can see we had a quiz. This was the quiz. All right, now, yeah, so questions.
Well, it was actually in this homework, one of the questions.
Okay, yeah.
It confused me. It was number...
It was this last one, so 7-3?
Yeah, I think it was number 19? No, number 17.
So let's see. 17?
Yes.
Okay, or no, okay, so number 17 from page 530. Make sure we are recording here. Should be. Yes. So this is page 531. Number 17. And these are alpha and beta are acute. And it gives you that cosine alpha is equal to 4/5. We know that tan beta is equal to 8/15. We are supposed to find all of these. We have sine alpha plus beta, cosine alpha plus beta. Okay, so we have sine alpha plus beta, cosine alpha plus beta, and finally, which quadrant? Containing alpha plus beta. Okay, so the quadrant. All right, so same way I did in class, I think the best way of dealing with this is to get triangles for these guys. Another thing, what I'm going to go ahead and just get up here on the board is just the regular old formulas for sine alpha plus beta, which is, it goes sine cos, okay, sine is the same, so we do a plus, so it should be alpha, beta, beta, alpha, okay? Now cosine goes cos, sine. Cosine is the opposite sign. You can't get away from it, right? And so this is going to be alpha, beta, or beta, alpha if you prefer. Okay, and then quadrant and all that. So I'm going to start by drawing a triangle with alpha as a right triangle with one of the angles being alpha, because it tells us it's acute, right? So alpha, that is an alpha, it doesn't look like an alpha. And so then if cosine is 4/5, what side is 4 and what side is 5?
The adjacent is 4.
Adjacent is 4. This one's 5, which means this guy's 3. I think. Let's double check that. It should be this case that 3 squared plus 4 squared equals 5 squared. That's 9 plus 16. Does that equal 25? Yes. Okay, so we're good. That's one of the ones I just have in my head, 3, 4, 5. That's one of the triangles. I can't actually do that fast. So the other one is beta. So again, acute angle. So this is a qualitatively accurate graph, excuse me. Now, if tangent beta is 8/15, what is 8 and what's 15?
The opposite is 8 and adjacent is 15. Okay.
So opposite over, so yes, tangent beta would be that one over that one, 8 over 15. Uh-oh. Darn. So 64 plus 15 squared.
17.
It should be 17. Okay. And I think we had one like that in the examples we did yesterday, or Tuesday. I will get to you in a minute, young man. So now, each one of these, we could just look here and replace it. So for instance, sine alpha should be what?
3 over, oh wait, yeah, 3 over 5.
3/5. So I'm just going to replace it right here with 3/5. And we're going to multiply here. What's cosine beta?
15 over 17.
There we go, 15/17. Sine beta
8/17.
8/17 times cosine alpha.
It's 4/5. Wait, yeah, 4/5.
Cosine alpha is, yes, 4/5. That gives us that. Yeah. Thought that sounded familiar. So what I'm going to do, I'm going to go ahead and skip down. We're going to forget about this. It'll just be nice to have it here. I wouldn't do this if I were doing this on paper, but just since we have a whiteboard, I'm going to do that. So 3 times 15, and okay, a bunch of different ways I could deal with this. I'm going to go ahead and just like actually compute it. 3 times 15 is what? Well, actually, let's do 5 times 17. I'm going to go ahead and get the denominator. That should be 35, 85. Is that right?
Yes. Yeah.
I think so. Yeah, 35 and 8. Okay. So that's all going to be over 85. So this here, this is what I'm doing. Ooh, this guy is equal to something over 85. I notice it's also going to be over 85 here. So I'm going to go ahead and just do it this way. That's 85. Right?
Yeah.
Right? The two denominators, I'm ultimately going to put them together. So 3 times 15.
It's
45, yep, so that's 45. It's going to be a plus 32. 8 times 4 is 32, yes. Okay, 32. So now, 45 plus 32. Something 7. 7? 77?
Yeah.
Is that right? Okay. So 77, oops, yes, 85ths. Okay, any questions about that? We got that.
I think in the back of the book, for one of the answers, it gave a negative number.
Ooh, okay, we'll see.
And unless I might have been a different one.
Let's just see here. This is 73, or 7.3, number 17. So we're here. We got the right thing so far.
Okay.
We're good so far. So here, let's do this. Oh, stop it. So, okay, we did all this and we got 77/85. Oh, buddy, just give me a second. 77/85. Okay, we just did these again, right? Like, we got all of these. So, I'm just going to, oops, well, okay, so it's cosine one, cosine the other, right? So cosine is 4/5. Cosine of this is 15/17. Minus, then it was sine, so 3/5. And then sine of that one, which is 8/17. Which again should all be over 85. 4 times 15 is 60.
Yeah. Wait.
Oh yeah. Yeah, 15 and 15 is 30. 2 30s is 60. Okay. So 60 minus 3 times 8 is what, 24?
Yeah.
Is that right? 24? 24. So 60 minus 24, it's not 40, it would be 34. Right?
36.
Thank you. Yeah, good. 85. 36/85. Does that...
Is that what it said in the back?
30, yep, that's what it says. 36/85. So you might have just been looking at the wrong thing.
Maybe.
So let's do that. 36/85. Now, what quadrant does that have to be in?
Wait. Oh, so sine is positive, so the top two, and cosine is positive, so the first.
There you go, right? That's how I would do it. I would say, well, if sine is positive, then your angle must be up here somewhere. And of course, you could say, well, with two acute angles, it's got to be in the top half anyway. But let's say we didn't know that. Maybe in general, we're not given that that's acute. And let's just say that this, in general, you have a plus b. Well, if sine's up here, it's one of these two. Cosine's also positive. Cosine's positive in these. So all of them, it must be quadrant 1. So it's quadrant 1. Boom. So yeah, maybe you just looked at the wrong thing. The next one, the one just below it has negative answers, so maybe you just looked at that and said, oh wait, I'm not getting the right thing. Yeah, maybe. So yeah. But that is your understanding of what's going on?
Yes.
Okay, cool. You could take your time figuring out what you want to talk about. This is going to get there in a minute. Oh, I know. I'm very well aware that you're not happy with the situation. You want to take it off yourself. What did you do with your sock? Here it is. Woof.
Okay. Number 57 in not this homework, the homework before.
The previous homework. Okay, so the previous section.
On page 519.
Oh, thank you. That helps. Oops, sorry. I might need to unbuckle you first. Huh?
Maybe 520.
Hey, yeah, you like that, huh? Okay, let's do this.
Let's not kick that. Thank you.
There we go. All right. I think we're good to go. Okay, so you said it was what page?
519.
519.
I think in my book, like, there's like a section of pages that are upside down. So
interesting.
It's
And which number?
57.
57. Okay.
That might be 520.
Yeah. 520. That was my, when I was in the Army, that was my unit. 5th Battalion, 20th Infantry. And so we had lots of jokes about things at 520, but like when 520 would roll around. Okay, so, ooh, whew, that one's ugly. Yeah, I can see why you have problems with that. Okay, so we're gonna have fun. So, and let me just make sure I know what this is telling me to do. It says, find the solutions to the equation that are in the interval 0 to 2 pi. Okay.
I think you have to like factor by grouping. I tried it like
Yeah. Let's just see.
I tried it like 5 different ways, and one of them might have been the right way, but I'm not sure.
All right. Yeah, this looks wicked hard. So this is page 520. Ooh. Page 520, and this is number 59. And we're finding all solutions.
I think it's 57.
Oh, I'm sorry. Well, 59 looks wicked bad too. Find all solutions in the interval 0 up to 2 pi, not including 2 pi. Okay. 57. Oh, yeah, you got, that's terrible. So, let's see, what's even worse? So, yes, factoring by grouping. So we have 2 sine cubed x plus sine squared x minus 2 sine x, and yep, I'm seeing grouping going on right there, minus 1 equals 0. So the first thing I'm going to do, I'm thinking, oh, this is a polynomial. You've already like said, you know, factor by grouping. So you're already assuming we're going to think about this thing as a polynomial, which, yeah. And I'm going to use the variable a. I'm going to let a equal sine x. So then this turns this equation into 2a cubed plus a squared minus 2a minus 1 equals 0. And now we have a cubic. And anytime you want to try to factor a cubic, really the only tool we have in our toolbox is factor by grouping. Well, like there are a couple others,
I didn't know which ones to put with. Like, the first one I did was 2a to the third with -1, and then do like a difference of cubes.
Yeah, and that's going to send you down a rabbit trail.
Because 2 doesn't.
Yeah, so okay, so let me, in general, there are a couple different ways we could deal with this. And let me show you. So usually you don't, when you're grouping, you don't want to group the highest and the lowest thing together. What you want to do is you could either group these together or, so group these together and group these together, or you group these together and these together. And I'll show you both different ways of doing it, and we'll see that we'll arrive at the same place. So on one hand, let's not move anything around. Let's just do the easiest thing, which is we'll just group those together. And if that were the case, if that were my polynomial, what could I factor out?
A squared.
I could factor out an a squared, and that would leave me, let's see, so I'm pulling out 1a squared, and what would that leave me?
2a plus 1.
Now, take a look at what's left over. Does that look like almost 2a plus 1?
So let's factor out
We would
-1.
need, if we factored out a -1, I'm not even going to write the 1, I'm just going to pull out the negative, and sure enough, we get 2a plus 1.
And then you can factor out to 2a.
Then we factor out the 2a plus 1, and to make this more visually appealing, I'm going to do that on this side over here. I'm going to pull out the 2a plus 1, like that. That is an a. And what does that leave over there?
A squared minus 1.
Yes, good. Leaving me an a squared minus 1. And every time I do this, I like to double check, and I'm going to say, wait a second, hold on. If I plug that back in, I would get that. Yep. Threw that back in, I would have a squared times that. Yes, I'm good to go. Can we factor further?
Yeah.
What do I do?
It's a plus 1 times a minus 1.
There we go. So we have
Oh. Yeah, I was trying to
a
do the
plus 1, a minus 1. There we go. And so I'm going to go ahead and I'm going to write that right here. And then we're going to do it a different way. So we have a plus 1, a minus 1, and then 2a plus 1 equals 0. Okay, so now let's say I didn't group it that way. The other way to group stuff. And one thing that's kind of suggestive about this way is to say, well, this has a 2 in it, and this has a 2 in it. So I know that if, at least if I group those together, I could get a 2 to come out. I could factor something out. So maybe I'll start that way. And I'll rewrite this as 2a cubed minus 2a. So I'm just swapping these guys around. Plus a squared minus 1, like that. And now I just start asking myself, okay, so those are the two I'm grouping, and I put them next to each other just so visually it'll look better. Now, what can I pull out of this group right there?
2a.
2a. So I'm going to pull out a 2a. And now we have a plus a squared minus 1. Okay, what's left over when I pull out my 2a?
A squared minus 1.
A squared minus 1. Up. A squared minus 1. And so now I'm going to pull out my a squared minus 1. So there's my a squared minus 1. And what does that leave me on the left?
2a plus
2a plus 1. There we go. Which is the same thing we got before, right? We would then take this guy and factor him down, and we would end up with this. So when I was first taught factor by grouping, I thought that there was a definite way you had to do it. That you had to identify something like this, like, oh, there's a 2 and a 2, so those are the ones that should go together. Or I think another way of doing it, like, so they suggest that you always group the third power with the first power, and you don't have to. The only real thing that you have to do is not take that one and that one.
So I just did the worst.
You did the one combination that wasn't going to get you anywhere. But I wonder, I mean, it's possible that, like, if you really plugged that along, you might have ended up with something.
But you'd have like the cube root of 2.
Right, you'd have the cube root of 2, which show up in there, and then square root of 2, and and then you'd be trying to relate that to what's left over in here, which would factor down to a times a minus 2. None of those show up there. So I think you'd probably just be chasing your tail forever. So the one rule of thumb with factor by grouping is don't group the largest and the smallest together. Although I don't know. I don't know. Something tells me that there is a chance that there is a case where that might work.
27 or something.
Yeah.
Or an 8.
Yeah.
Something that could.
Something that is right, and it might just work out that way. But usually, what you want to try first is one of those, and like I just showed you, either way you go is going to work. Even though it might not look like it will, it should work. But sometimes one way is easier than the other, but yeah. So now we have three equations. Basically, we can turn this into 3 equations. Either this is equal to 0, that's equal to 0, or that's equal to 0. And so from there, and let's just for the sake of completeness, let's just work the rest of this out. I'm sure you know what to do from here, but let's just do it. So we have that a plus 1 is equal to 0. So in other words, a is equal to -1, but a is sine x. So we have sine x is equal to -1. And now what's nice is we're only looking for solutions between 0 and 2 pi. So we could say, and another nice thing is this isn't 3x plus 2 or something like that, right? Like we're just saying, well, there's this graph of sine x, and we could just graph it on that interval and say, okay, where is that one equal to -1? Well, that occurs right here. So what's the value?
3 pi.
So here we go. X is equal to 3 pi over 2. That's one of them. The other one is a minus 1 is 0, so that a is equal to +1. But that means that sine x is equal to +1. And where does that occur on the interval of concern?
Pi over 2.
At pi over 2, yes. So just to be clear, this was because this is 3 pi over 2. This, which is 1, occurs at pi over 2. And now here's the tricky one. 2a plus 1 is equal to 0. So solving, we get that 2a is equal to -1. A is equal to -1/2, so that sine x is equal to -1/2.
Pi over 6. Oh, wait, basically.
Yeah, and so now I could see that we are getting, we should get 2 answers. There's -1/2, and, oh, stop it. And so that's going to occur in 2 places. One here in which quadrant, and one here in which quadrant?
In the 3rd and 4th.
There you go, in the 3rd and 4th quadrants. And so, what triangle is going to give us sines 1/2?
Pi over 6.
Yeah, it should, yes, exactly. So we have 1, 2, root 3. This is pi over 6. Sine of pi over 6 is 1/2. But now, another way of doing this is to just say, okay, well, where are all my pi's over 6? Well, here's 1 pi over 6. Here's 5 pi over 6. Here's 7 pi over 6. And what's that last one?
11.
11 pi over 6. And so we know that this is occurring in the 3rd and 4th quadrants, and so it must be this one and this one. And so this little nifty equation gives us that x is equal to 7 pi over 6, or x is equal to 11 pi over 6. And so that should be all the solutions in 0 to 2 pi. Cool? So yeah, I know like the problem, the hang up you had was with the factor by grouping. But I did want to just do this just to be complete. It's nice to go through this kind of stuff too. So, okay, any other questions that you might have? This could be anything from any point in this class or previous classes. I mean, we got time, so.
There was one thing that's just sort of confused me. It wasn't really from
Okay. Give me just a second, because I just remembered, I told Mrs. Burry that if Victor did have questions and he wasn't going to show up, to email me. So I'm just checking my email to see. He does have questions. All right, excellent. Okay, so since he's not here, forget this guy. What's your question?
It had to do with I. So it was just something like, I think it was last year when I was doing one of the homeworks.
Okay, so then, yeah, we'll do Victor's questions first, and then we'll come back to the fun stuff.
Yeah.
Okay, so let's see what Victor says. He says, when you prove some kind of trig identity, is it acceptable to plug in some value and prove that it is equal or not equal, instead of trying to manipulate a side until it works? When you have to prove some kind of trig, when you have to prove some kind of trig identity, is it just as acceptable to plug in some value, like pi over 2, and prove that it is equal or not equal, instead of trying to manipulate the side until it works? Here's an example. So let's say we're trying to prove, we want to know, is f of x equal to g of x? And so I say, okay, it turns out that if I plug in a 0 into f of x, I get out a 1. And if I plug in a 0 into g of x, I plug in a 0 into g of x, I also get a 1. So my question to you is, can we conclude that f of x is equal to g of x? No, because what if they're not the same? What if
cosine
f of x, well, let's make it even easier. Let's say that f of x is x plus 1. And let's say that g of x is x squared plus 1. Are those the same thing? No. Absolutely not, right? But it happens to be the case that when I plug in a 0, I get out a 1 from one of them. Plug in a 0 into this one, I get out a 1. But if we really, if we want to look at this thing, what does this look like? Well, g of x looks like this. F of x looks like this. And so we're going to get a couple places where they both agree. So I could plug in a 0 and get out the same value because they're good there. There should be another place. Where would they be equal? I guess 1, right? Yeah, plug in a 1. If I plug in a 1, so going back to the original question, you say, well, can I just plug in a value and find out? Well, we plugged in 1 and it was good. Why don't we plug in another and see? Let's plug in f of 1 is equal to, I plug in a 1, I get out a 2. G of 1, plug in a 1, I get a 1, and it's equal to 2. So I'm like going double of what you're asking. Like, can I just plug in a value and see if they're the same? I'll do 100% better. I'll say plug in 2 values and we find that they're the same. Are they the same function? No, they're not, right? They just happen to match up here. What you would have to do is check every single possible number, every real number, plug it in and see if they work, to see if they're equal. Now, but this is probably where the confusion is coming from. So when you want to prove that 2 things are indeed equal, you need to manipulate and show that they're equal. But to show that they're not equal, all you would need is just 1 value. Because for instance, if I plugged in a 3 and said, well, f of 3 gives me a 4, but g of 3 gives me 10. Immediately you could say, well, no, they can't be the same function. Because if you plug in a 3, you get a 4. If you plug in a 3 on this side, you get a 10, so they can't be the same. We don't need to go through and say, well, f of x is actually x plus 1. G of x is actually x squared plus 1, right? So this is why to disprove, to show that something's not equal, you only need 1 value to show that they're not equal. Because if they don't agree at that one value, well, they can't be equal everywhere. And this is kind of what all these trig identities are about, is you're asking, are they equal everywhere? Because there's a bunch of places where they are going to be equal. Let's just think about sine and cosine. Is sine equal to cosine? Is sine x equal to cosine x? And you might say, well, let me plug in a pi over 4. Sine of pi over 4, is that equal to cosine pi over 4? And so you say, well, hold up, pi over 4 does this. 1 root 2. So sine of pi over 4 is 1 over root 2. Cosine of pi over 4 is 1 over root 2. Oh, yeah, so they're equal. Well, no, they're not. But let's say you continued on and you said, well, what about 9 pi over 4? And so, or what about, what would be another one? Well, let's actually graph these guys out. Because what's going on here? We have sine, which does this, and goes on forever and ever and ever. And then we have cosine, which does this, but you'll notice that these things do intersect. They intersect here at pi over 4. They intersect down here at, what would that be? This would be pi. So the next one beyond it, I guess 7 pi over 4? No. 4 pi over 4, 5 pi over 4. Thank you. At 5 pi over 4. They would intersect again at 9 pi over 4, and so on and so on and so on. So, in fact, you could find infinitely many values. Like, I could go and argue and say, well, hold up. You're asking me, is sine x equal to cosine x? And I say, well, plug in pi over 4. Yeah, they're the same. Plug in 5 pi over 4. They're the same. Plug in 9 pi over 4. They're the same. And I could go on and find you infinitely, buddy, he needs a crawl. I could find you infinitely many values where they are equal. And so you then, by that logic, you should be able to conclude that they're equal. No. So the crux of the matter here is to show that something is equal, you need to actually manipulate. The reason that we're manipulating is we're, in effect, checking all infinitely many values. If you could turn one side of the equation into the other side of the equation, then it must be true for all possible input values. But if you're trying to show that something's not equal, then all you need to do is find one value where they don't agree. And I could say, well, what about pi over 2? And so I plug in sine pi over 2, and I get out a 1. I plug in cosine pi over 2. I get out a 0. Since they're not equal at this point, then they can't be equal everywhere, so we conclude, no, they're not the same. It's not an identity, etc., etc. So I hope that clears up the confusion. And I can see, because I remember in your homework, you didn't make that mistake until after you had done the disproving part, where the prompt said, find a value that contradicts this, which this would be a good one. And then in the next part, you had to find out whether or not it was an identity. You found one part that proved it, and so, yeah. But this is the crux of the matter. You might actually find infinitely many points where they do agree. In other words, where they both equal the same thing, and so that this equation is true even at infinitely many points, but that doesn't prove that they're the same function. So, I hope that makes sense. If you were here, I would say, does that make sense? But you're not here, so, yeah. Okay. Came out with the homework we just made. Can you have sine, or cos? Or plug in the results in tree. Okay, yeah. So, here's the question. This came up on the homework we just did when I made a mistake. Good. He said, can you have sine of sine? And he didn't put an x, but I'm going to put an x, because I'm sure that's what you mean by that. Or cosine of cosine? Like, is that possible? Can you do this? Cosine of cosine? Is that possible? Said I plugged the result into Desmos, or I tried plugging the stuff in on Desmos, and the results intrigued me. Yes, they should. And let's just think about this. So the first question, can you have this? So let's think about this. This could be a great question. What's the domain of this guy?
Wow.
Like, is this possible?
All real numbers.
Should be, and let's just check that. My intuition says all real numbers. It should be defined everywhere on the real line. And let's see if that's true. So first off, we look all the way in and say, is there any problems with plugging x into sine? No, it's defined on all real numbers. Okay, so then you do that. You plug something into sine, and what pops out are values between 1 and -1. Okay, so then we say, well, can I plug that into the outermost function? Can I plug values from -1 up to 1 into sine? Sure, we could do that. So, in other words, this is what I'm doing. Again, this is not standard, but I hope you understand what I mean by that. Like, if you were to plug in all those things from that interval, you're going to get some values. And let's just think about what that range would be. So if sine does this, goes up to 1, down to -1, and it's between pi over 2, which is approximately 1.4 something, and it comes down to -1 here at -pi over 2, and that's approximately -1.4 something. Then 1 is about here, -1 is about here. So we're just going to be plugging in values that bounce between here and here into sine. And so we should see something that bounces between, say, 0.8. I have no idea if that's at all accurate. And -0.8. That's just my intuition. And so our final thing should oscillate and maybe do some crazy stuff. I don't know. But it's absolutely possible. And in fact, in signal processing, if you want to send a signal to someone, so like radio, radio is a signal, right? If I want to send a radio transmission to somebody, or you turn on the radio, you have AM and FM. AM stands for amplitude modulation, where the height, the amplitude, like we've talked about, the amplitude of the wave is what carries the information. FM is frequency modulation, and what you do is you modulate the frequency with your signal. The way that's done is you take you could do it with sine, but you do a cosine curve, and what you plug in is something of this form. X plus C, we'll say. Something like that. And actually, I think it is. You could look this up on like Wikipedia. I actually think that's what it is. And then as you vary B with time, your thing changes. And so this is actually, this is something that is done like quite regularly. And so yeah, it's yes you can. So yeah, to answer your question, the long-winded answer, yes you can. No! Oh, of course he did that. Of course he found that. Buddy, let's try not to do that. Let's try not to pull, nope. Here, why don't you practice standing? Check this out. Oh. Here, practice standing. There you go. Yeah, here, figure that out. All right. All right, this will be interesting. Oh yeah, that's my book. Oh boy. Okay, so sine of sine pi gives you a horizontal line. Yeah, because you didn't plug in a variable. So when in Desmos, if you just write in 5, it interprets that as y equals 5, and then it just gives you a line that goes through 5. So if you did sine of sine x, it would plot the stuff, but if you did sine of sine pi, Desmos is going to take that and say, well, what is this? It's just a number. It's going to say sine pi is -1. And so then it's going to say, well, what is sine of -1?
Wait, isn't sine of pi 0?
Thank you. Yeah, whoops, wrong thing. Thank you, I was thinking cosine. It's just 0, but sine pi is just 0. And so it says, it gave me a horizontal line at y equals 0. Because when you plug this in, when you plug it in with a value, it treats it as the number that it evaluates to. So when you plug this in, Desmos interprets it as y equals this. And so if you wanted to graph sine of sine x, you'd have to give it an x. Or a t, I think Desmos can handle that. But when you give it an actual value, it's just going to interpret it as this. And it says ditto with cosine. Cosine pi gives you a line at y equals 0.54.
Yeah.
So cosine of cosine pi is going to say cosine pi is -1. That's the one I was thinking.
Yeah.
Cosine of that, let's think.
Cosine of -1 is just...
Cosine of -1, so this is at -pi/2, which is about -1.4 or something. And so -1 is right there, and so it comes out to be about 0.540, what did you say, 3. And so Desmos interprets this because you've given it an actual value, and it just interprets the actual output. And it just says, well, that's what this is. And then it just graphs it for you. So if you wanted to actually do it, if you want to see what the function looks like for any given value, instead of giving it a number, ooh, nice, number to evaluate, you give it a variable. And then it'll interpret it for every input value x. You could play with that, that's fine. Okay. I'm glad you didn't get hurt. Okay, now let me just see. Why is this happening? Well, that's why it's happening. Give it a variable and you'll see some interesting stuff. That's all I can think of for now. Won't be able to come to class. I was wondering if there might be there after class, give you the homework. I don't want your homework. Keep your homework. Just keep it. I don't want to see it.
I think I already gave it.
No, you did. You did. Just saying. Okay, and here's this quiz. Looks good. Okay. Okay, yeah, play with that. That's a good thing to play with. Have fun. Okay, so your question. So wait 1 second. Is there anything else I want to say? Yeah, play with this. You go put this into Desmos, and then mess with the values of A, B, and C. So when you plug this into Desmos, like as you write this, it'll say add all or something like that. Add all A, B, C. And if you just hit enter, you'll get sliders for A, B, and C, and they'll all go between. Why? Oh, that's my book. And it'll all go between like -10 and 10 by default or whatever. Slide those things around and see what happens to that. It's really cool. So have fun. Okay.
He's messing with it.
Oh man, dude! Just don't knock it over. Vinny! Ben! Alright.
How old is he?
He is 8 months now. He'll be 9 months on the 27th. Let's stop that. Let's just stop it. Okay. Okay, so what was your question?
It was just some, so if you take the square root of I to the 4th.
The square root of I to the 4th. Okay. Okay, so we have I to the 4th.
Which, yeah, the square root of.
And we take a square root of it. Yes.
And so I to the 4th, well, that equals 1. Right?
Okay. So let's do this.
Because of the like, it's like.
All right. So let's do it this way. Okay, yeah. So you're saying that that is just 1. So it should just be like this. Okay.
Yeah. But then also I to the 4th is I squared times I squared.
Uh-huh.
And then you could write it as, wait, let me write this out. It's like
yeah.
square root of I squared times I squared.
So let's do it this way.
Which then you could write as the square root of I squared times the square root of I squared.
Which would just be I squared, right?
Which is negative.
Which is negative 1. So remember now, let's say we have some number that equals I to the 4th. Now let's take a square root.
Well, it'll be plus or minus.
Aha.
But, well, when you plug in, so that I plugged in I to the 4th equals negative 1 onto Wolfram Alpha, and it said it wasn't true.
You plugged in what? I to the 4th equals...
The square root of I to the 4th equals negative 1.
Right, so this is what's going on. When you take a square root, this is what happens here, right? So let's continue, right? There's two possibilities. Either, so you have a number, you've taken a square root. You have two possibilities, so that either the square root of x, which was your original number, is equal to positive I squared, or the square root of x is equal to negative I squared. Now, the square root of x is either equal to, what's this? Negative 1. I squared should be negative 1,
Yeah.
last time I checked. Or the square root of x is equal to negative 1. What is your deal? Or it's equal to negative 1, which should just be positive 1.
Yeah.
But in both cases, this isn't what we asked about. We're trying to figure out about this number right here, right? We want to know what is x equal to.
But you can...
And so here we don't have really a problem, because either way, in neither of these equations do we have x. And so forgetting everything above this line, let's say I just presented you with this, and I said, what does x have to be? How would you, in this case, what would you do there to get? You'd square both sides. Doing that gives you x equals 1 squared, which is just 1. In this case, you'd square both sides. That gives you x equals negative 1 squared, which is just 1. In both cases,
But you can...
look at that. So now, what are you saying? What are you noticing here?
You can prove that the square root of I to the 4th equals negative 1 without taking the square root.
All right, one second. You could prove that, say that again?
The square root of I to the 4th equals negative 1 without taking a square root, so then
Okay.
it wouldn't be the plus or minus, right?
Wait a second. You could prove that sorry, I'm trying to do this while using my brain, and I think I'm using too much RAM trying to get this boy into here. Come here, boy. Come here, boy. All right. Okay. You could prove that the square root of I to the 4th is equal to what?
Negative 1 without taking the square root.
How? So let's see.
So it's...
Okay, so you're just saying we're starting here.
Yeah.
Okay, let's start there, and let's see what we can come up with. And then we're going to go into, so this is kind of, everything I've done up to this point is pretty standard, but we're not really touching at what's really going on with complex numbers until we draw this on the complex plane, that's what we'll do next. So, you're saying we have some number, and it is equal to the square root of I to the 4th. Now you're telling me that that is negative 1.
Yeah.
I believe you, actually, because what I'm going to say is this is, well, you're taking the positive square root, okay, no problem. That's the same thing as raising this thing to that power. No problem. So I'm going to then use this, right? Multiply, because if you're taking something raised to a power,
yeah,
right, we multiply those. 4 times a half is the same thing as 4 over 2. And I'm going to say that's that, which should be negative 1.
Yeah.
And so then x, just as written, but this is the thing about this symbol here. It's what are you asking about? Like, what does that mean, right? And what is the context? Like, because in an equation, if you have an equation and you're manipulating it, like we were doing before, then it's like, well, wait a minute, there's two possibilities, because you're taking a square root. It could have come from two different places. So, whoa, now what, right? In this context, we're just saying there's some number out there that can be written this way. And what would that mean, I guess, is that it has the property that when you square it, the square of that number is equal to I to the fourth. But I to the fourth is equal to 1. So there's a number out there that obeys that law right there. There's actually two numbers that obey that. There's a -1 and there's a 1, right? And so by having it written this way, you're kind of choosing one of them, right? Does that make sense? Like, because whenever you take a square root, now you have the context of both possibilities in there. And so you write that little plus minus out front. But now here you've already chosen, stop it. Now you've already chosen one of them. And so, boom, it gives you that. But on the other hand, like you said, isn't this the same thing as this? Right? Right? And so you'd say, well, the square root of 1 is 1. But is it? Because, wait a second, now back in context, you're saying that there's some number out there, and when you square it, it gives you 1. Well, yeah, there's two possibilities now. Right? So, this is the thing about it, is that square root thing is hiding a lot of work. And it is ambiguous as to which one of these things you're talking about, right? There's no way around that, because like that's just how square root works. And even when we don't write the plus minus, when you're saying this thing just exists out by itself, it's like, well, no, not really. I mean, it kind of does, but it kind of doesn't. And so, remember what squaring does to a complex number? If we think about, take any two complex numbers, say this one, let's take that one, and let's take this one, plus I times 1 over root 2. Sorry about the i's. I wrote them one way and one of them the other one. So, two complex numbers. One lives here at the real part, 1 over root 2. And the other one at positive 1 over root 2, I. The other one is just the same thing, but now the x part's negative. And we said that complex numbers have this interesting property that if you take this angle, that if you wanted to multiply these two complex numbers together, let's call this one z, let's call this one w. If you take them and multiply them together, z times w has the property that you add the angles, right? So angle, this is theta for this guy. This angle here will be phi for that guy. What is theta, by the way? Think about if that were a triangle. What would the sides be?
Wait.
So let's do it this way.
Oh.
This guy lives here.
Oh.
That base would be
1/2.
1 over root 2. 1 over root 2.
Yeah.
The height would be
1
1 over root 2.
I.
And what would that be?
Square root of 1 over 2 plus 1 over root 2.
Wait a second. Pythagorean theorem. Square that.
Oh, it's, yeah, the square root of 1 over 2 squared plus 1 over 2 squared.
Equals what number squared?
1/2. Oh, just 1. Oh, 1.
Another way you could think about this is this triangle, 1, 1, root 2, but it's just been scaled down.
Oh,
In fact, right, like I just divide everybody by 1 over root 2, and I get that. So then what's this angle right here? Pi over 4. So, okay. So it's pi over 4. Now, this one, you'll notice, like I haven't drawn it very well, but this angle is the same as that angle, which means where does he live if we're talking about like actual...
It's 3 pi.
Yeah, because 1 pi over 4, 2 pi over 4, this would be at 3 pi over 4. So, and also, what's the length from here to here?
1.
It's also 1. So, what we talked about last year was that if you multiply two complex numbers, you add their arguments, or you add their angle measures. And so what's 3 pi over 4 plus pi over 4? Pi. It's just 4 pi over 4, which is just pi. So this thing should be at pi, and its magnitude, or modulus, we call it modulus. Its modulus is what you get when you multiply those two numbers together, the two moduli together. So that means 1 times 1 is 1, and so it should be 1 unit in the direction of minus, or in the direction of pi, which should be right here. Okay, so, oops. Here's pi. Here's 1 unit, so it should be here at -1, right? Are you following so far?
Yeah.
Because this is just review, basically. But now we have some actual angles and some trig stuff that we could talk about to kind of fill this out. Okay. So I took apparently the number z times w should be -1. Because we're just talking about how do you get there. One way of talking about how to get to a point on the plane is to say you go that many units right, that many units up. This one says you go that many units to the left, that many units up. Another way of saying it is go 1 unit in the direction of pi over 4. Another way to get to that point would say go 1 unit in the direction of 3 pi over 4. One way to get here is to say go -1 units left. Another way of saying it is go 1 unit in the direction of pi. And let's just check what happens when we do this with these guys. Z times W is actually equal to, so Z is 1 over root 2 plus 1 over root 2i. W is 1 over root 2, no, I'm sorry, minus 1 over root 2 plus 1 over root 2i. First outer, inner, last. -1/2. Outer gives me 1/2 I. Inner gives me
-1/2 I. Oh, cancel it.
And the last gives me what? -1/2, because we have 1 over root 2. 1 over root 2 gives me 1/2. I times I is -1, so it should be minus that. Those guys cancel, and I get that and that. It's -1/2, -1/2. These guys are gone, and I get, oh, what do you know? -1. Now, here's the question. If I wanted to take the square root of this number, so, wait, well, I'm jumping the gun. Sorry. So, okay, that's cool. What happens when you square a number then? And we're going to forget about this guy over here. We could go back and do that guy. But let's square a number. Here's z, and I want to see what happens when we get z squared. Well, that's the same thing as taking z times z. And the rules still apply. We should just be able to take the angle, add it to, in this case, itself, right? The angle of this guy, or the argument of this guy, is pi over 4. Argument of that guy is pi over 4. What's pi over 4 plus pi over 4?
Pi over 2.
Pi over 2, right? So it should come up to pi over 2. And then in both cases, the modulus is 1, so it should be 1 times 1, which is 1. So it should be that when I square this guy, I get pi over 2. I run a distance of 1 in the direction of pi over 2. And that should put me at, on the complex plane, 1I, or as we just call it, I. But now, then if that's the case, if z squared is equal to I, then when I take a square root of it, wait, shouldn't I get a plus and a minus?
Wouldn't it be the square root of negative? Wait, the square root of... Oh, yeah.
Right?
Yeah.
Right? And so that's what I'm saying, right? It should be the case that the square root should bring me back to where I started right there. And that's exactly what that is, by the way. But somehow, wait, we still can't escape this. It should be negative, that thing, too. Like, we know that this is the positive square root of I. Obviously, it's positive because that's positive and that's positive. But it says that the negative one should work as well.
But negative, wait.
So negative that would be this guy down here. He would be at negative 1 over root 2 minus 1 over root 2I. So wait a second. What happens if I double that? Right? Because that's what we did here. We started here. We squared it. So let's call this guy W. This is some number W. And I'm wondering, because it says here that z, well, if this works here, I double the, given a number on the complex plane, if I want to square it, one way to do that is to just straight up square it out. And we didn't do that, did we? Let's do that. Let's check our work here. It should be the case that if I take 1 over root 2 plus 1 over root 2I, and I multiply it by itself, 1 over root 2 plus 1 over root 2I, I should get I, because that's what this tells me, right? That's what the angle and argument, or the argument and modulus thing was. So first, outer, inner, last. I get first is 1/2. Outer,
1/2 I.
1/2 I. Inner,
1/2 I.
plus 1/2 I. Last,
1/2 I squared.
yeah, which is
Negative 1.
negative 1. So this guy and this guy cancel. And I get 1/2 I plus 1/2 I is just, oh, plain old I. Nice. But there's another way to be on the plane and have this property. And it's if it's negative. And let's see what that means. We're just going to take this number, z, make it negative, which is what I did. I just multiplied it by negative 1. Everything's the same, even though it's a complex number. If you want to make a complex number negative, you multiply it by negative 1, which makes this part negative and that part negative. And now, let's forget everything we just did, and let's just square this number and see what happens. And let's do it in the same order that we did. Let's find its argument first. Where does this guy live?
5.
There you go. 5 pi over 4, because this is 4 pi over 4. We know that this is like how, like just by symmetry, obviously, if that's pi over 4, that has to be pi over 4. So we're at 4 pi over 4. This would be 5 pi over 4. Okay. And what's its length?
1.
1, right? It's the same coordinates. It's just that one went this way and one went that way instead of one going this way and one going that way. Okay, so 5 pi over 4. Okay, let's square it. What happens when I square this number? We get 5 pi over 4 plus 5 pi over 4 is how many pi's over 4?
10.
So 10 pi's over 4.
5 pi over 2.
Which is 5 pi over 2. And what's so? And the argument or the modulus The length of that joker right there is 1. And so when we do w squared, we get 1 times 1 is 1. So this tells me to go a distance of 1 in the direction of 5 pi over 2.
Which is the same as pi.
Ha ha! Look at that, right? Because you have 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, and we go a distance of 1, we should end up at I. And let's check it. Let's check it. Let's see what happens. This times this. This times itself. So we're computing w squared now explicitly. First is a negative times a negative, which is a positive, which is just 1/2. Root 2 is a half. Or, outer, a negative times a negative is a positive. So positive 1 over root 2 times itself is 1/2. I, there's only one I, so there's an I. Inner, negative times negative is a positive. 1 over 2, I. Last, negative times a negative is a positive.
But then the negative.
But then I times I is negative. Lo and behold, it's the exact same thing. 1/2 and 1/2 is just, oh, look at that. So this is kind of my point with all this, is you cannot get away from, when you talk about a square root of something, there's always going to be two numbers on the plane which will, when squared, come back to the same point. Yeah. And so that's what a square root is. You're asking, you know, like, we did all this work. We started here, and then we squared it, we ended up here, but we could have just said, if you're here, and you know that it was something squared, where did it come from? Well, you could always say, just take half of that. But there's also more than that, because this thing just keeps wrapping around forever and ever. In fact, I mean, if you want to be like pedantic about this, you could say, well, yeah, pi over 4, 5 pi over 4, 9 pi over 4, whatever that would be. 9 plus 4 is 13 pi over 4, and so on and so forth. And but now we're not talking about unique points in the plane anymore, right? But as far as, but yeah, so this is kind of what I was saying. Like, you can't get away from it. You're always going to end up with two possible values. And even what's I? We said that I to the 4th should live right there, because I to the 4th is 1, right? And so you could say, what's the square root of that thing? Well, there's two ways that you could have gotten there. Either, you know, if your angle, you could think about this thing as, well, its initial angle was 0, so half of 0 is 0, it stays put. Or you could think about it as, what's the initial angle? Well, it's 2 pi. So what's half of 2 pi? Bring it back. You're back down to -1. You just can't get away from it. There's two places on the plane that, when you square those places on the plane, they will map to that point right there. Does that make sense? Yeah. Does that answer your question?
Yeah.
Yeah, and so this is what I mean by square root. It's like you're saying, well, I have this. I'm not talking about plus or minus. I'm not talking about operating on an equation. I'm just talking about what is the square root of something. Well, there's two possibilities. It could have come from here, or it could have come from here. So really, that plus or minus is always with you, no matter what. So, any other questions? This could be about anything. You know, just like this one, right? This weird stuff. And bet you didn't think we'd be doing trig with that, did you? No. And this is another thing I mean. Like, trig is so fundamental to everything you do from here on out, that it's like, if you, like I was able to just dream up these numbers, right? I mean, I could have used, you know, instead of using this as my reference angle, I could have used pi over 3. And then I'd say, well, hold up, pi over 3. And I'm thinking back to my triangle, right? If this guy's pi over 3, this guy would be pi over 6. I know that that's 1, 2 square root 3. But if I don't want to have to deal with multiplying this. I would like it if my hypotenuse were 1, so I'm going to go ahead and shrink everybody. And so I'm going to end up with 1/2. There's 1. That would be root 3 over 2. And so I could have started with this point on the complex plane, and I would have called it 1/2 plus root 3 over 2I. And we could have just played that game and said when I square it, it'll come over to here, which should be minus 1/2 root 3 over 2I. And then we square it and you go, how did you know that it worked? Like when you actually plug it in and do it, it actually worked. Well, because I know this stuff, right? And it's like, this will make your life so much easier like as you go on, because this kind of stuff pops out, and the better you have a grasp of this stuff, the better. So